Welcome, curious minds, to another deep dive. Today, we're plunging into a truly fascinating and, well, somewhat perplexing corner of the world of large language models, LLMs. For a while now, we've heard these incredible stories about their reasoning prowess, particularly in complex areas like mathematics. And that skill is often said to be boosted, significantly amplified by techniques like reinforcement learning. But here's where the plot thickens and things get really intriguing. Recent studies have surfaced with claims that are, frankly, quite eyebrow-raising. They suggest that certain models, specifically those in the Qwen 2.5 series, could potentially improve their math capabilities even with minimal supervision, or maybe even more surprisingly, with random or even incorrect reward signals during reinforcement learning. Now, for anyone familiar with how reinforcement learning is supposed to work, that sounds, well, almost like magic, doesn't it? Especially when other big models like Llama just don't show these same weird gains.
Right. It's a phenomenon that has truly puzzled the research community, and for good reason. Reinforcement learning fundamentally relies on precise, accurate feedback to guide a model towards, effective training and improvement. The idea that random or even completely inverted reward signals could somehow improve performance for one model family, like Qwen, while offering little to no benefit for others like Llama, well, it immediately raises a critical question. What could possibly explain this stark discrepancy? So our mission today, based on the source material you've provided, is to really dig into the empirical analysis that sheds light on these seemingly unreliable results. We'll try to uncover whether this indicates genuine novel reasoning or perhaps something else entirely. By the end of this deep dive, you should have a much clearer understanding of what's truly at play behind these surprising claims.
Okay, let's start by unpacking this unusual claim then. Researchers observed that the Qwen 2.5 model family showed significant improvements on pretty well-known mathematical benchmarks. We're talking about datasets like Math 500, AMC, and AIME, which are sort of the standard tests for evaluating mathematical reasoning. And the puzzling part was, these gains appeared even when the reinforcement learning process was fed, well, faulty or random guidance.
Yeah, it's quite counterintuitive. In a typical reinforcement learning setup, if you give a model bad feedback, say, you tell it a wrong answer is right, or you randomly praise incorrect steps, you'd expect its performance to get worse, right? Or maybe to stay flat. Yet with Qwen, these benchmarks showed an upward trend. So this led the researchers to come up with two main working hypotheses. The first was that perhaps Qwen inherently possesses a remarkably strong baseline in math skills, making it unusually receptive to any kind of learning signal, even noisy ones, almost like it could learn for anything.
Okay, that's one idea. And the second hypothesis, which sounds a bit more suspicious, maybe, was something called data contamination. Can you elaborate on what that means here?
Certainly. Data contamination suggests that because models like Qwen 2.5 are pre-trained on absolutely massive web-scale data sets, I mean, we're talking petabytes of information, including huge code repositories like GitHub, educational forums, academic papers, just everything. It's highly plausible that these models might have inadvertently encountered some of these benchmark problems and, crucially, their solutions during their initial training phase, way before the benchmark test. If that were the case, then the model wouldn't actually be acquiring new reasoning skills when it performs well on the test. It would simply be recalling or, reproducing answers it had already seen. Think of it like a student who accidentally gets a copy of the final exam answers before the test. Their performance on that specific exam wouldn't really reflect their understanding, would it?
Right, that makes sense. So if you suspect data contamination, how do you even begin to test for something like that? It feels like finding a needle in an enormous digital haystack, given the scale of pre-training data. The researchers had to devise a pretty clever approach, I gather, to measure what they termed the model's memorization capability, using two key indicators.
That's right. They focus on two main metrics, the partial prompt completion rate and the partial prompt answer accuracy. The method involves feeding the model only a portion of a problem, let's say, just the first 60% of a math question. Then they'd observe two things. First, could the model accurately complete the remaining 40% of the question text itself? And second, once the question was complete, could it then provide the correct answer? To measure completion, they used metrics like RUGEL, which basically evaluates the overlap of text sequences, an exact match, which, as the name suggests, requires a perfect character-by-character match. And for the answer part, they just used answer match accuracy.
Okay, and this is where the investigation really started to reveal things, leading to some, well, Pretty striking findings, as the source puts it.
Yeah.
On benchmarks like Math 500, when Quinn 2.5 Math 7b was given just that partial prompt, only the first 60% of a question, it showed this almost uncanny ability to regenerate the rest. It achieved an impressive 54.60% exact match rate for completion. Think about that. More than half the time, it could perfectly reproduce the rest of the question just from seeing the first part.
And maybe even more telling, despite only seeing an incomplete prompt, Quen 2.5 Math 7b still answered 53.6% of these problems correctly. That's over half. The sources give a really powerful example. When prompted with just, for how many positive integers n1 is, which is just a fragment from a Math 500 problem, Quen 2.57b accurately reproduced the full question. 224 is a perfect nth power, and then gave the correct answer, 7. It even generated a complete step-by-step chain of reasoning to get there. Now that level of completion and accuracy from an incomplete prompt, it strongly hints at prior exposure, doesn't it?
Wow, yeah. In stark contrast, what happened when they tried the same thing with Llama 3.18b?
Well, when the same partial prompts were fed to Llama 3.18b, its scores on these same metrics were dramatically lower. We're talking 3.8% for exact match completion and just 2.4% for partial prompt answer accuracy.
That's a huge difference.
It is. And this difference isn't just quantitative, it suggests a fundamental divergence in how these models were interacting with these specific data sets when partially prompted. Llama didn't seem to have that same kind of memory recall trigger.
So that was strong evidence, but maybe not definitive proof yet.
It was strong initial evidence, yes, but the definitive confirmation, the real sort of clincher in this investigation, came from evaluating the models on new post-hoc benchmarks. These were datasets compiled after the Quen 2.5 model family was publicly released. That means there was absolutely no possibility of them being included in Quen's original pre-training data. Live Math Bench is one example they used.
Okay, so the moment of truth.
Yeah.
What happened when Quen faced these truly novel problems on Live Math Bench? Problems it definitely hadn't seen.
On Live Math Bench, Quen's partial prompt completion rate dropped sharply, all the way down to 0.0%.
Zero.
Which was entirely consistent with Llama's performance. Llama also scored 0.0% on this measure, and Quen's partial prompt answer accuracy also plummeted, down to just 2.0%, which again was now comparable to Llama's 1.0%. This evidence really solidified the hypothesis. The earlier, seemingly miraculous gains seen on the older benchmarks like Math 500, they weren't due to new reasoning capabilities being unlocked by weird reward signals. They stemmed from content Quen had memorized. Its prior success under random or incorrect rewards seems to have just inadvertently triggered the model to retrieve answers it had already seen and stored away during its massive pre-training phase.
Okay, that paints a much clearer picture. So if the older standard math benchmarks were effectively compromised by this data contamination, how did the researchers design a test that could truly assess a model's inherent mathematical reasoning ability, specifically in the context of reinforcement learning? They needed a completely clean slate, right?
Exactly. That was the next really clever step, creating a completely fresh, leakage-free dataset. This innovative dataset is called RandomCalculation. It's automatically generated, which means it can construct unique arithmetic expressions of really any length and difficulty on the fly. And the key design feature is that every single problem instance in RandomCalculation literally came into existence after Quen 2.5's public release. This setup guarantees there's absolutely no prior exposure for the model. It forces genuine computation, not recall.
A truly clean test, then. And the results on this meticulously clean dataset must have been quite revealing about how reinforcement learning actually impacts Quen when memorization isn't a factor.
They were unambiguous. When Quen 2.5 Math 7D was trained with reinforcement learning purely on random calculation, a very clear and frankly expected pattern emerged.
Okay, what did they find?
First, when provided with only correct reward signals, proper feedback, the model showed steady, consistent performance improvements. In fact, it actually managed to surpass its initial performance ceiling in mathematical reasoning. It showed genuine learning was happening.
All right, that makes sense. What about the weird signals?
Second, and this is crucial, when the model was trained with random or incorrect rewards, the very conditions that appeared to improve it on the contaminated benchmarks it's training became highly unstable. It showed no reliable improvement whatsoever. This directly contradicted those earlier spurious gains. The magic disappeared on clean data.
In the inverted rewards, where it was penalized for being right.
Well, as you might intuitively expect, when given inverted rewards where correct answers were penalized and incorrect ones rewarded, the model's mathematical reasoning ability rapidly declined. It was actively being taught the wrong thing, and, well, it learned it Performance tanked.
So that finding seems pretty pivotal.
It absolutely is, because it effectively rules out that initial hypothesis, the idea that Quen's prior magic was due to some inherently super strong baseline math skill that let it benefit from any signal, however noisy. Once data contamination was removed, once that memory crutch was gone, the seemingly inexplicable gains just evaporated completely. It really underscores the critical, indispensable role of accurate and consistent reward signals for genuine learning and improvement in these large language models. Without clean data and proper feedback, any observed progress could just be a phantom, an artifact of memory.
So this brings us to a pretty fundamental question then.
Oh,
What does all of this ultimately mean for Quen 2.5? Does it possess genuinely strong mathematical abilities, or is it more of a sophisticated memorization machine when it comes to these benchmarks?
well, it's a bit nuanced. The research does indicate that Quen 2.5 does possess strong inherent mathematical capabilities. That seems clear from its performance on the clean random calculation dataset. When it was provided with collect reward signals, Quen 2.5 Math 7b was not only able to learn, but actually surpassed its initial performance. This demonstrates it can effectively transfer its high-accuracy single-step arithmetic skills to more complex multi-step calculations. It can genuinely compute and learn.
Okay, so it can do math. But the crucial distinction here, the real takeaway, is that while Quen is certainly capable of learning and improving with proper, accurate guidance, its prior apparent success with random or inverted rewards on those contaminated benchmarks was not due to this intrinsic strength. It was almost entirely due to the model just retrieving and reproducing memorized answers. The mechanism was recall, not new computation.
That's the key difference, precisely. This research strongly suggests that for us, as researchers and developers, to draw dependable conclusions about how well reinforcement learning methods work and about the true reasoning capabilities of LLMs, it is absolutely essential to evaluate them on truly uncontaminated benchmarks. And furthermore, consistently testing these phenomena across various model families is critical. We need to avoid making broad assumptions based on what might just be a unique data exposure quirk of one particular model or training run.
Yeah, this deep dive has definitely given us a different perspective on how LLMs learn, and, maybe more importantly, how we assess their intelligence. It's clear that these impressive surges in performance we sometimes see aren't always what they appear to be on the surface, especially when we're dealing with models pre-trained on the vast, largely unfiltered sea of data out there on the web.
I think the takeaway for you, our curious listener, is the paramount importance of data integrity and the quality of the feedback. It's just fundamental. This applies not just to how we train these increasingly advanced models, but fundamentally to how we evaluate their true capabilities.
Yeah.
What we feed them and how we tell them they're doing profoundly shapes what they actually learn, or perhaps what they just appear to know.
So what really stands out to you from this whole exploration, perhaps the striking fact that a model could perfectly regenerate half a math problem and solve it purely from memory, that's kind of wild, or maybe the powerful, undeniable role of truly clean data in teasing apart a model's genuine reasoning skills versus just sophisticated recall.
Moving forward, I think this research suggests we should all remain vigilant in the AI landscape, always questioning the source and the nature of impressive results. Ensuring our evaluations are built on solid, contamination-free ground isn't just good scientific practice, it's absolutely essential for understanding real progress in artificial intelligence, separating the signal from the noise.
Definitely. And maybe a fascinating thought for you to mull over, if even cutting-edge AI, like these LLMs, can be inadvertently led down the path of memorization by subtle patterns in the data they were trained on, what does that tell us about the importance of critically evaluating the information we consume every single day? How much of what we think we know is reasoning versus recall?